This meeting is being recorded.
Question?
I don't know why not last class, the class before, there was no audio.
Uh-oh.
Yeah, video. I just want to
Hopefully, I think there should be audio right now. Yeah, must have forgotten to press that button. Sorry about that. How's everybody doing? Is there a lot of midterms going on right now or other stuff? Just one, sort of. Thank you. I did it myself. You can probably tell in the back if you. Just with the razor, the roomy thing, whatever that thing's called. Yeah, I do feel weird spending $25 to just for a haircut, but I really don't like the waiting in line and all that stuff associated with the barbers. And well, I mean, I could, but that requires just thinking in advance about things, and so it's simpler and easier, but maybe uglier, but simpler and easier if I just do it myself in the bathroom here. I usually do it once my kids start pulling my hair, then I trim it down to the point where they can't pull my hair anymore.
It's like, I can't remember his name, but there's this record executive who cuts his hair once a year. Once a year, he shaves it all and goes completely bald and throws it all back. It's to experience the full life cycle of hair every year.
I used to do something similar, like definitely not more than once a semester, and I wouldn't go all the way down to like pick it down to the skin, but I can't let it grow out now because the kids pull my hair in it, so I have to cut it more often.
It's defensive.
It is, yes. Okay, let's see. So we're in class here. Topic 6 grammar stuff. We'll be finishing, I think, today everything that we need to do for your homework assignments. And there's 2 of them due this coming Sunday, the arithmetic one and the esolang one, which is like a superset of the arithmetic that contains the arithmetic inside of it, plus some other stuff. The main goal of the arithmetic one was to get you familiar with so both writing these grammars so that you can go on to use like llama.cpp or whisper.cpp in order to write interesting grammars for those things. But then the arithmetic in particular, focusing on these transformer classes and doing these transformations, converting one abstract syntax tree into another without doing computation. One of the key things about these transformer classes is that they just do translation without computation. And they're doing it from the leaves to the root. If you're going from the leaves to the root on one of these abstract syntax trees, then you're not able to do computation. But this esolang one is going to be using the interpreter class everywhere instead of the transformer class. And the interpreter, the way the recursion happens is from the root down to the leaves, and that increases the amount of power that you have as you are working through the abstract syntax tree, allows you to do interesting computations. For example, like actually evaluating a for loop or implementing recursion or if statements, things like that. And a lot of those things, some of those things already implemented for you in the esolang code here. Last time we started talking about how to do if statements. We'll finish up talking about that today. And then the main part of your homework will be implementing while loops all on your own from scratch. You also have to fix a little bit of brokenness in the for loop. So that'll be the if statement here, and doing this fix in the for loop will get you all of the preparation you need for the while loop there. I'll switch over to the code here in a second and see if there's any questions that people have before getting started. But before doing that, one of the things that my overall sense of people in the class is that there's maybe like, whether this feels interesting or not interesting, it feels maybe somewhat disconnected from the stuff that we were previously talking about. And We've had one connection so far in terms of if you're able to write these grammars, you're able to use whisper.cpp, llama.cpp to constrain your output. And that's a useful thing, but it's not the only connection that's going on here. Another connection that was more along the lines of the things that I like to think about is about like what are transformers, what are large language models, LLMs, in principle able to do. And in principle, the one of the important things that we talked about up here is this idea of a deterministic grammar. And we didn't go into the definitions of these different types of grammars other than all three of these things happen to be context-free. But programming languages in particular are deterministic, and they're guaranteed to be able to parse in linear time. And they are therefore things that could potentially be implemented by a transformer. I want to talk a little bit more about this connection here. And in order to do that, I'm going to come over back to our RASP paper. And the RASP paper actually talked about this in quite a lot of detail, and we kind of glossed over it, didn't talk about it at the time. So here in the paper, the thing that I want us to take a look at is this third paragraph in the paper, and I'm just going to basically read it off for us here. And it says, so thinking in terms of the RAS model can help derive computational results. So these two previous citations explore the ability of transformers to recognize these DeQ languages. So the DeQ languages, again, are these languages of balanced parentheses, and they are somehow the most fundamental languages in this context-free realm. And that if you can do the DeQ languages, then you can probably do every other context-free language. And it's been a very important question for linguistics and computational linguistics in particular about what is the power of large language models to recognize these DeQ languages, because it sheds a lot of light on what sort of language processing that they can do. But continuing on here, one of the things they say is, so using RASP, we succinctly express the construction of that citation as a short program and further improve it to show that for the first time that transformers can fully recognize DeQ for all K. And so this is a very important thing in order to be able to understand these papers, in order to be able to understand why, what is the power of a large language model, whether it's based on transformer or something else, what is its power. Understanding these grammars and what languages can and cannot be supported is a very important part of that. So continuing sort of off of that vein, there's another topic 7 posted. And this is going to be basically the remaining last topic for this course. We're just going to talk about a whole bunch of papers that I think are interesting. And there will probably be no more programming assignments related to any of these papers. The main purposes of all the programming assignments that we've had so far, including the ones that are due this coming week, is been to prepare you to have the background to be able to read these papers, to be able to talk, to be able to understand what people in the LLM community are talking about when we talk about the capacity and capabilities of these models and how to improve them and their directions. So we will be mostly focusing on these papers for the rest of the semester. Since there will be no more programming projects, this will give you plenty of time to work on your actual project. And again, you should be spending roughly 3 to 5-ish hours per week on that project. You have a little bit over a month left to complete that. And again, this week, your rubric for the project is due. Again, that rubric, the high-level idea is that that's your contract between me and you about what you have to do in order to get an A on the project, and therefore probably an A in the class. And so you want to make that as clear and detailed as possible so that we are both on the same page. And if you post that, send it to me, then I will give you feedback about whether I think there are things that you should change or whether it's good as is. Yeah, so for each of these papers below, read it before the designated class. We might spend one or we might spend two classes on each of the papers, depending on how things go. Suggesting 3 hours reading the paper. These papers will be definitely hard and technical, more so than the previous one that we read for the most part. And again, I don't expect you to understand everything, but make some effort to work through the difficulties you encounter. There's not going to be any sort of evaluation on this. It's not going to affect your grade at all, but this is really the part of the class where you're most likely to learn the most amount of useful material for you in the future, being able to actually understand what other people are talking about transformers and predict what the direction of the field is going to be. Since we're this week talking and last week talking about these interpreters and transformers, the difference between these two classes in the Lark Python module, the way I think that you should be reading is you should not be inside of the transformer mode where there's no computation going on in your brain. Your brain should be like in interpreter mode, actually doing computation as you're reading the language. And these classes, because they're about the papers, won't be recorded, so that's, I don't know, I'm more free to talk about whatever. And I don't think the recording is as helpful when talking about the papers. The recording's more helpful doing programming related stuff, so you can go back and see if you missed some piece of code or something. So these classes won't be recorded, and so please be present on time. Only one paper posted so far for Wednesday, this on the ability and limitations of transformers to recognize formal languages. It is the citation right here that RASP talks about why these DEEK-K languages are important. And so this is what the paper looks like. It starts off with this pretty picture up here about different powers of languages. And so we'll talk on Wednesday about what this picture means, what the details are, and why it's important for our understanding of large language models. As a hint, one of the things that this paper discusses is how quantization in the llama.cpp, whisper.cpp documentation, there was probably a lot of discussion about quantizing models, and we'll be able to, after working through this paper, understand one of the effects of quantization and how it is going to reduce the model's ability to do certain things based on grammar. Okay, I said a lot of things there. Takeaway is that for next class, we'll be not doing any more programming stuff, focusing on starting on this paper, and that your homework assignments due this weekend, and we will finish talking about this esolang assignment today. Any questions about anything administrative or where we're going or what we're doing? Question is, when is the rubric due? And I think the actual due date that I gave was probably today, but there's no, I don't know, no hard deadline, just earlier is better. Yeah. Your goal should be have it finalized with me by the end of the week. That would be, if you do that, you're still on track time-wise for things.
And that first paper, we're supposed to be published November 4th.
Wednesday, yes. Wednesday is not November 4th. Wednesday is November 6th. But yeah, that's what we'll do. Start on that next class. Okay, everybody's good? Everybody's awake? Everybody had a good weekend? Cool. Everybody wants to dive into some Python here? Yes, okay. So here I have my two windows open up. PWD, present working directory. I'm in my esolang directory here. And one of the things that I want us to do really quick, which we haven't done yet, is talk, well, we have talked a little bit about this main.py and what it's doing. Let's look at it in some detail to remind us what's going on here. And I'm going to do a big reminder of things that are going on here, touching in different ways, the things that we talked about last time. So it's a mixture of review and new material, so that we spent a whole weekend since we talked last time to get ourselves back up to speed. So on the right-hand side over here, I opened up this main.py file, the double underscore main or dunder main or magic main. All those pronunciations are acceptable in the Python world. And the purpose or the reason that this file exists inside of esolang is I can do now Python 3-m esolang, and the -m right here in the Python 3 executable means that we are passing in a module, m for module. And in Python, a module is essentially a directory, and so esolang here matching this esolang directory. And again, a Python convention is that inside of a repository, my repository's name is esolang. Inside of that repository, there's a folder with that exact same name, and the folder with that exact same name is where all of the code is being located. And the purpose of the double underscore main file is so that if we want to run a module directly, that is the code that will be run. And so I can hit that and run it, and we get the esolang prompt over here, and I can do things like 1 + 2 like this, or I can do print, it doesn't support strings. I can do print 1 like this, and we'll print the number 1. And I had chaining ability with semicolons to provide multiple commands on the same line, something like this. One of the things that this interpreter does, which is nice, that the RASP interpreter does not do, which was not nice, is allow you the ability to use the up arrows to go back and forth like this. In Python, this is really easy to do with this readline module right here. Anytime you're implementing your own environment that is sort of like a REPL, something where you can be typing in commands, using this readline library is a very good thing to do. You don't have to do anything special after you import it. Just importing it by itself, saying import readline, means that anytime your input function down here, anytime you use it, it's going to allow you to use the up arrows to go back and forth between commands. Press Control-D on the left-hand side to get out of that environment. Comment out readline up there, rerun this, and now I'm pressing the up and down arrows, and these are the actual, what they're called escape codes on the terminal. They're being sent by my keyboard, and so you don't get that feature of being able to go up and down. RASP did not do this. They had some weird workaround where you had to run this script, and it wrapped the Python executable inside of some other program that provides this readline-like functionality. That was one of the things, one of those clues that told me that Gail Weiss, the author of RASP, was not like a Pythonista by training, that she, and I know this also from the fact that she went to an Israeli university, that she is really a C programmer by training. They don't really care about Python over there. They do everything in C. And it showed in many ways, one of those being that she did this really complicated workaround instead of just this one line import readline right here. Okay, but yeah, so we're inputting, this input gets us our command, and then you always use the parser.parse to compute the abstract syntax tree or the parse tree of that command. And then here calling this interpreter on interpreter.visit on that tree to do the computations. And then besides that main.py, we had four other files in here, level 0, 1, 2, and 3. And each one of those files develops some more functionality for this language that we're working on. The level 0 arithmetic right here is the same as the arithmetic assignment. And then the statements, loops, and functions adding more features onto the language. If I do vim esolang star.py-p, I can open them all up at once. And so here I'm in my arithmetic file. This grammar is something we've seen a lot now, so that's very familiar. Here I'm in the statements file, and there's a bunch of test cases up here at the top, and then another grammar down here. Each one of these level 0, 1, 2, 3, and 4 files, they define their own grammar, and they define their own interpreter class that defines the semantics of that grammar. The semantics of something, again, is like the meaning behind it, whereas the grammar is just whether it's valid, whether you get a syntax error or not. And so each one of these levels adds new grammar rules and new semantics for those grammar rules. Last time we were working on this statements and looking at the grammar down here, trying to add the if statement ability to that grammar rule. And we were using the way that I decided to do it is to use what's called the ternary operator, this question mark, where we have the condition to the left-hand side and the question mark, and then whatever the true thing is immediately after the question mark, and whatever the false thing is after this colon character right here. So I'm going to take away the numbers so we can fit a little bit more on one line, set no number. So this grammar rule right here defines the if statement for us, if statement condition, question mark, start, colon, start. And we also modified our start rule. We modified the start rule right here so that the if statement was a new valid thing that could appear. The previous version of this did not have the if statement. We added it in there, and we added the if statement rule down here, defining the syntax or the grammar of what if statements look like. But we haven't yet talked about like the semantics of if statements and how to do those. Any questions on anything from last time or from this time or from anything at all yet? This thing that I'm highlighting right here, this is the actual grammar definition. So it is LARC code or grammar code or EBNF code inside of a string, inside of the Python file. The LARC syntax says that comments will start with a hashtag like this. So all of this was comment describing what the meaning of this if statement is supposed to be. But this right here, this is the actual line of the code that matters, of the grammar that matters. This is what defines what the format of the if statement actually is. Good question. Any other questions so far? Okay. Then to the rest of today in class, I'm just going to go through and implement the semantics of this if statement right here. And as we do that, we'll see various debugging techniques that will be useful for you as you are doing the same thing for the while loop and the for loop. So the first thing I want to do is let's just double check again that my if statement semantics are working, not giving me any sort of error message. I'm going to go on the left-hand side over here. Let's see, let's clean up my screen. I'll reset that and up arrow, get back to my Python 3-i esolang / this is in the level 1 statements right here. And if I do this, let's see, on the right-hand side, well, we'll do just this. We'll do tree equals parser.parse and 1 question 2 colon 3, something like that. And I do not get a syntax error if I do this. But if I say forgot the colon like that, then I get this crazy syntax error like this. This is a syntax error not at the level of Python, but at the level of LARC. And it's telling me that this string that I passed in right here is missing that necessary colon, or it's missing some sort of computation happening on the tube right here. This expected one of means that any of these things down here would have been valid characters, valid tokens, valid things for me to type. So colon was the one that I took away, and because there's nothing here, it's ungrammatical. So that is what that is now grammatical once again. And we can, another thing that we talked about before is we can do add these code blocks inside of here. So if my if statement is going to do more than just return a single number, we can actually do some computation inside of it. We can put those inside of code blocks and say something like a equals 2, and then a plus 3, something like this. And this code block, if we have one of these code blocks, the semantics of this code block is that the last line is always like a return statement. This whole thing will evaluate to whatever the last line is equal to. So this whole thing right here would evaluate to 5. We also said that for our if statement, to simplify things, we're not going to implement Boolean variable types. We could, it's not hard, but the reason I'm not doing it is just to stretch your minds a little bit more and do everything with numbers over here. And the way we'll do it is the conditionals represented again as numbers. So the thing to the left of the question mark is the conditional. This is the thing that is going to decide whether we do this right here or this right here. And if we will use 0 as true, so this right here is not 0, so it is false in our language because non-zero things are false. 0 is true, non-zero things are false. This is the opposite of Python, but it is the way that the C language and most Unix systems, most languages actually, interpret true and false.
Is there a reason why?
Is there a reason why? There are good technical reasons about how computers worked in the 1970s that made this the simple thing to do.
Is there a reason why like Python is true?
And then the question is, why did Python switch to 1 being true? The answer is that's more mathematical. That if you have 1 being true, you can think of multiplication as and addition as or, and
So it's
everything
like some
goes through
rules and
straightforward.
stuff like that.
Yeah. Yeah, good question. Okay, so that's all the grammar stuff. Let's think about like how to actually get this, the interpreter part here working. And again, this interpreter class here, anything that semantic-wise feels like it needs an interpreter, this is going to be beyond the scope of things that a large language model is able to do. That the large language model able to do these sort of transformer-ish things, but not able to do these interpreter-ish things. So the if statement, anytime we have our, well, let's visualize the tree again. Let's remind ourselves how to do this. Let's come back over here. Anytime we have one of these trees, visualizing these trees, we can just print them out directly like this, or doing something like print tree.pretty like this to get the a little bit easier to visualize version of this tree. And let's simplify our tree too, take away this block. And so our tree, we have this if statement right here. There's this condition, and then these 2 start parts, and then the start and the number like this. Actually, it's a little bit annoying to me. Well, I'll do that in a second. So we're starting from the top down here of this tree, and we're traversing into our subtrees. And so we need a node inside of our interpreter for this this if statement node right here. We already have a node for the start statement because our interpreter right here is it's derived from this level 0 class right here. The level 0 interpreter is the base class for this interpreter right here, and the level 0 interpreter has a start function defined right here. And so by deriving from this, we get all of those other functions for the level 0 arithmetic stuff sort of for free. So our interpreter in the statements already contains the start and the number and the add and all of those things. And we just need to add the new features to the inside of this class for our new, the new grammar rules that we've added. So again, in Python, a convention, these double underscore magic methods come first. These single underscore methods are different than the double underscore methods. The double underscore methods have built-in semantic meaning inside of Python that every class is going to have some sort of init method, and this is somehow special to Python. If we have a single underscore, this is not something that is special to Python, but this is something that is special to my implementation of this class. It is a method or member function of this class that is not designed for external people to use. It is designed only for the class to use internal to itself. Another way of saying this is that this is not part of the public interface to the class, and you should not use these member functions of classes unless you really know what you're doing. And then there's a whole bunch of nodes down here that do not have the underscores in front of them, and each one of these corresponds to one of the grammar rules. I will put my if statement at the top of these over here. The top of the set of functions that are the public interface of this class. And these functions will get called as we are traversing. When we're at the start node and we visit the child, the visit function will call the appropriate function inside of the interpreter class over here. And so we'll have an if statement like this with self and tree. And I'm just going to, this is a thing I often do when I'm doing stuff in Python, is just to add some garbage code right here just to force the Python interpreter to crash, so that I know that if I get here, the Python interpreter is going to crash. And let's see, another thing, interpreter equals interpreter like this. So this lowercase interpreter now is my instance of this uppercase interpreter class, and I can do something like interpreter.visit of tree like this to actually evaluate the tree. I haven't reloaded my code over here since I added this, so it did not actually call this if statement method, but I'm going to press Control-D on the left-hand side over here to get out of Python, up arrow to re-get back into Python. I'll press my up arrow to recreate my tree right here, up arrow to recreate my interpreter, up arrow to that recreated the tree, reinterpret the tree, and now we get this name error, name ASD is not defined because we're calling this node right here and immediately causing Python to crash. The key thing about what we're going to have to do, though, next is actually implement this if statement so that it does, in fact, define the correct semantics of what an if statement is supposed to do. Any questions, though, about where I'm at, what I've done so far? All right, so I'm intentionally going on the slower end of things right now. Definitely slower than if I were coding things by myself. Just to try to make sure that people can mostly follow along with what's going on here. It's easy to get confused with all the different things, all the different moving parts that are happening here. But also, there's maybe a danger of if I go too slow, then it's hard to pay attention and stay focused. So people feel like there's a good pace so far? Or?
I think we should build an application that keeps like a live tracker that like displays on the screen where we all like input live judgments to speed, so you can know exactly how fast we go.
Mm-hmm. Your faces are that live tracker.
Yeah.
Okay, so the if statement right here, this tree, again, another very useful code debugging thing that I do all the time in Python. When I'm in like coding mode, I probably add this thing into my code, like, I don't know, many times an hour as I'm working on things. This is my #1 go-to tool for debugging complex things. And this is importing this code module inside of Python and then doing this code.interact, which jumps me directly into a new Python interpreter. And I do this so often that I have a hotkey on my computer set up just to put this in here. So import code and then code.interact. This local equals locals right here specifies what the variables are going to be. That they'll be whatever the local variables are to this function will be the local variables in my Python interpreter. So let's redo that. And also to make my iteration a little bit faster over here, I'm going to temporarily copy and paste these things down to the bottom of the file so that I don't have to re-add them into the Python interpreter every time I want to work with them. So this tree equals parser.parse. I'll have some sort of parse tree always to work with, and some sort of interpreter always available. that I can apply to that parse tree. On the left-hand side, Control-C, Control-D, up arrow, restarting a new Python terminal with this file with all the changes that I've done. The tree variable now is in existence. The interpreter variable also in existence. I can do interpreter.visit of tree like this. And when I hit enter, you can see that I am now in a new interactive console in Python. I still know that I'm in Python because I still have as my system prompt over here these 3 greater than signs. But you can see that after I ran this line right here, there's a whole bunch of message that'll be a little bit different for your computer, but a whole bunch of message going on right here that tells me that Python has now started up, and I'm in an interactive console session right here. And now I can type tree right here, and this tree is different than the tree that I saw before. The tree that I saw before, again, had a little bit longer, starting with a start node up here, and this tree that I have now does not start with a start node, it starts with the if statement right here. The if statement is the root of this tree. Again, I'll visualize this in a slightly nicer way of print tree.pretty like that. And so this is the tree of the if statement. This is the thing that I have to define the semantics for. So up here in the if statement, this is the thing that I have to define the semantics for. This is the thing right here that is the variable tree right here that's being passed into the if statement. Question is, why does if statement come before start? This is a great question. That on the left-hand side, I'm going to press Control-D right now. When I press Control-D, that exited this interactive session right here created by the import code and went on to the next line right here, ASD, which terminated the program right here. And now if I do the same line of code of print tree, we can see that there is a start up here at the very root. And it is the case that for this tree right here, it begins with start. But for this tree right here, it does not begin with start. The tree that is being passed into your function, the tree, whatever that function happens to be, the way Lark is structured is that the root of this tree right here will always be whatever the appropriate, or whatever the name of the function is. That the function is being called based on the root of the tree over here. And so the root of this tree is if statement. Where we're getting to this if statement from is inside of the start right here. There's a for every child in the tree.children, visit that child. And so this call to visit on child right here, that child is this subtree right here without the start. This start only has one child. Every one of those children will be visited, have the appropriate code called on it, and so it calls the if statement. I think last time, 2 times ago, at some point we did this for the arithmetic assignment, the interpreter, this start node here. A good question, yeah.
Is code interact local equals locals, the OG debugger breakpoint?
Yeah. So that's if you've used debuggers before, this is Python has a better debugger built in called DBG, I think. But I find this to be easier to use than a regular like debugger with breakpoints because I can just use my standard Python knowledge to do stuff instead of having to know Python and know another debugger. So debugger is a little bit more powerful, allows you to step forward in time and manipulate things in a little bit more complex ways. But this is, basically a debugger light that's easier to use and reason about. And so it's what I always use. Does that answer your question? Okay, so now that I know the structure of what's being passed into my if statement over here, I can start thinking about actually implementing this if statement. And the first thing I need to do is I need to evaluate this condition and determine whether it's going to be equivalent to true or equivalent to false. And let's see. I'm going to rerun my interpreter.visit over here, get back into this tree right here. And so let's pretty print it. So I'm in the tree with the if statement at the root. I'm in the location right here where whatever code I type into Python on the left-hand side is going to be equivalent to the code that I put in and on this line in my actual code. And I can think about how do I actually, like somehow I need to access this number one. I need to access what is the value of the condition over here. Or if more generally, like do all of this computation and give me the results. And so if I do tree.children, children will generally be the thing that you'll want to be working with when you're creating one of these member functions over here for the interpreter. And tree.children is going to have 3 elements inside of it: the condition, and then the true start and the false start right here. And the one that I'm most interested in at this point is the condition, to know which one of these 2 nodes down here I should evaluate. And so I have to figure out how do I get access to this, this condition right here. And because it is the first thing in my list right here, the first one of these elements that appears, it's going to be at position 0 in the children list like this. I do that, and this gets me the condition tree up here. Let's see, let's go ahead and pretty print that as well, dot pretty. And so we get the condition start number 1. In order to actually do the computation on all this and see what does this evaluate to, I have to do the self.visit. So it'll be self.visit of tree.children of 0. Again, children of 0, because I'm interested in this condition part, which is the very first entry in this list, the 0 entry in this list of children of if statement. And I do that, and it does this computation of giving me this list 1 right here. Why is it inside of a list? It's because currently there is this condition statement right here, and there is no condition implemented inside of this interpreter class. Anytime you access a node that is not implemented in the class, the default implementation just passes the visit function onto all of the children and puts the results inside of a list. So the default implementation of this condition node right here will call visit on its child, which happens to be start, and then put that inside of a list. In this case, a list isn't strictly necessary because there's only one child, but in general, there could be more than one child, and so that's why a list is used to pack this information. Two ways that I can go about fixing this are, one, I can add an actual condition child over here, an actual condition method, def condition self tree, and do something here. That would be one thing that I can do. But a simpler thing to do is to go up to my grammar and remember that in my grammar, anytime I put a question mark in front of a rule, then Lark will not include that rule if it only has one child. And in this case, that's reasonable behavior. I don't want this condition to actually be its own separate thing. I'm not going to do any special computation for conditions. I just want to get straight to the computation, which is represented by start. And so adding this question mark right here is a simple thing to do. It will remove this condition from the tree, remove this node from the tree, making my computation simpler. So the only meaningful thing that I did here was adding a question mark in front of condition, and we'll see exactly how that affects things. So on the left-hand side, Control D to exit out of Python, up arrow to get back into Python, and on the right-hand side again, Shift G to take me to the bottom. I have this tree that I'm still working with, that tree, and I can do my interpreter.visit of tree like this. And now I am in the if statement. My tree has this if statement right here. And if I do the tree.pretty and print that, then we can see that the condition portion of that top if statement, that condition portion of this first child of the if statement no longer exists. It's been removed so that we only have the start here. And now if I can go back to my visit command in the Python terminal, if I press Control R, it allows me to search through my history and actually in my esolang environment too, because I did that import read line, it allows me to search through the history as well. But I do control R. I'm looking for the visit command, interpreter dot visit, something like tree dot children of 0 is what I want. Not interpreter, I want self.visit because I'm inside of the interpreter class right now. Self.visit tree.children of 0. Tree object has no attribute children. Spelled correctly, not children of 0 like that. And now I get the 1, which is what I was getting before, but now it's not contained inside of a list. So this is the thing that I will use inside of my if statement in order to actually get access to the condition. Condition equals self.visit tree.children of 0. I'm gonna save that on the right-hand side over here. On the left-hand side, Control D, up arrow, get my interpreter.visit tree again. So this is the command that does all of the processing. And now at this line of code, my import code right here, and I can check that condition is in fact set the way that I want it to be. It's set to be 1 now instead of undefined. Any questions about that, Avizer?
When I run Python 3 minus R esolang level 1 statements of py, I get the import error. How did you get over that?
Yeah, question is, let's see, in order to reproduce this, I will just go ahead and create a new shells 1 topic 6 level like this. And in order to create my PS1, PS1 equals that changes my prompt. So this is the same setup that I had before, but now when I do Python 3-I esolang level 1 statements, I get this module not found error about no module named esolang right here. And in general, in Python, one of the things that I find frustrating about Python is that it does not look in your current folder for these modules. It only looks for modules that are installed system-wide when you do an import statement like this. The reason for that is complicated compatibility issues with Windows and Unix, getting them both to work the same way. In a consistent environment, Python decided to hide the entire file system from the import. The import system doesn't know anything about the file system. And so in order to fix that, you have to do an export Python path, all in caps, equals dot like this. The dot means that this is your current folder that you are currently in, and this tells Python that when it does do an import, instead of looking just in the system folders where things are installed, it should also look in wherever your Python path is, which in this case is your current folder. And so now if I hit enter on that and rerun this, then it is able to import that and able to see it. Yep. A lot of small, odd things about Python like that are easy to stumble upon. Any other questions so far? Okay. I'm going to do something next, which is the obvious way to implement if statements, but also the broken way to implement if statements. And this will be important for how you'll have to implement while loops and fix the for loop program. And so what I'm going to do next is I have my condition up here, and my condition is accessing whatever the 0 position child is. And we'll call this branch T, or we'll go ahead and do branch true. This will be access the 1 position, and then branch false, accessing the 2 position over here. And then I will add an if statement if condition equals 0, then return branch true, else return branch false, like this. So do the computation, get what the true value is, what the false value is, and so again, 0 is our signal for true if condition is 0. So if we're actually true, by our semantic definition of what true means, then we'll return the true branch. Otherwise, we'll return the false branch. And this will, it'll mostly work, but it'll have some subtle bugs in it that we'll have to figure out. In order to see how this is going to work, I'm going to go back to my -m version, esolang, and do the code in the interactive environment over here. And we'll try something like 1 2 :3 again. So again, the 2 over here, this is supposed to be the true branch. The 3 over here is supposed to be the false branch. And the 1 over here is our condition. In this case, the 1 is not truthy. It is not true. And so we will evaluate the thing on the right-hand side and get 3. And if we change this 1 to a 0, then we evaluate the thing on the left-hand side and get 2. And so this, in some sense, does implement if statements, but we're going to see a bug in this implementation here in a little bit. Is any questions about the semantics of what this is doing and why this is correct right now? Maybe do another example. So I can put complex math statements over here. Do something like 1 - 1 (2 :3). This over here evaluates to 0, so it does give me the 2-hand side over here. And I can put complicated-ish statements like let's see. We'll do a = 2, a + 3, like that, and we'll get 5 right there for this. We'll evaluate to create a variable a, set it equal to 2, and then add 3 to it. So all of these examples are correct so far. These are doing what it should do. But we're going to see here in a second examples of bad behavior. Everyone agrees these are all correct? This makes sense? Question?
Yeah, this is the first example. Why is it? What's after? Because 3 is after the colon.
So here, the thing to the left of the question mark is the condition, and since it is not 0, it is false. 0 is the only truthy value in this language, and so because it's a 1, it is false, which means we do the thing after the colon. So here, because it's a 1 here, we get 3. If we change that 1 to a 0, then we do the thing before the colon, which is a 2, and so we get 2. Okay. So the problem here is that, so first recall that we have a little print function that we can use here. And let's see what happens if I do 1 print 2 print 3 like this. And if I do this, then I get both 2 and 3 printed. I get both 2 and 3 printed. That this question mark here right now is currently what it's doing is it's evaluating both of these expressions, evaluating print 2 and evaluating print 3. And the result that it returns is the results of this one, but it actually does the computation for both of these two things. So this implementation of if statements right now is actually doing the computation for both the true branch and the false branch, giving me both a print 2 and a print 3. And that is probably not the semantics that we want to have in our if statements.
This is what RASP did, right?
Yeah, great connection. This is exactly how RASP implemented their if statements. That in RASP, they branched on both sides, fully implementing them. And it turns out that this pattern or this semantics can be implemented with the transformer class, and everything that with the transformer class can be implemented with the interpreter class. But this is not the semantics that you usually want from an if statement. And so we need to do something different in our interpreter over here to get the correct semantics. The difference, or the thing that we need to do, is right now on this if statement over here, we are currently doing this computation always. Like this branch true right here, it's always visiting its children over here, no matter what. Branch true, always visiting its children, no matter what. And because of that, it is, if the child is print 2 right here, it's always going to compute print 2, even if it shouldn't, even if we only want to do the evaluation on the right of the colon over here. It's doing the true condition, the true statement over here, even if the condition is false. And so adjusting this so that the branch 2 only takes place inside of the condition equals true, and the branch false only takes place inside of this else statement like this, is an important thing to do. Now, based on this condition over here, we're only going to, we're not going to go down both of those branches, not going to visit both of those branches. We're only going to visit one side of those branches. We're only going to either visit the true or visit the false. Save that, come over here on the left-hand side, Control D, get me out of my esolang, up arrow, hit enter, and now I will copy and paste this same command right here like that. And now it is in fact only giving me the print 3 on the right-hand side over here, only giving me the 3 and not doing the print 2. If I change this so this one is a 0, then it's only doing the print 2 and not doing the print 3. Any questions about that?
Yeah, this is just about this kind of if statement. Is there ever a reason why you want an if statement that evaluated both all the time?
So the reason RASP chose to do an if statement that evaluates both all the time is because their if statements were at the level of constructing the transformer, and the transformer, one of the properties of the way the transformer is constructed is that it has to evaluate both conditions when you have an if statement. Because for some nodes, some tokens it might be true and some tokens it might be false.
Oh, and it needs to stay the same way.
And it needs to stay the same length the whole time. So yeah, you're very much handicapping yourself if you have a language with semantics like this, but sometimes the point is to handicap yourself, and so you want that semantics. No real like modern language that people actually use has this semantics, but a lot of sometimes called domain-specific languages, RASP being very, very specific, but other things that are not that narrow will also have this sort of semantics. Good question. So for your homework, you're going to have to implement the while statements. And part of implementing the while statement, so basically 2 parts, is first defining an appropriate grammar up here. And there are many different ways that you could define a reasonable grammar for a while statement. You can choose whatever grammar makes sense to you. And then defining appropriate functions down here for that grammar that will actually do the interpretation of that while statement. And you'll have to be very careful in your function down here that you're calling the visit down here only when it's strictly appropriate, that you're not calling it too many times or too few times. And that's really the main trick of that implementation is getting these calls to self.visitCorrect. For the for statements, so it's inside of the loops over here. The for loop, you can look at it as a, a starting point for the while loop. It'll look very, very similar. And you can see that there's some sort of for loop down here with the self.visit inside of it. And so you can use this as a starting point for your while loop. The for loop over here is currently broken though, because the grammar up here has very limited things that it allows. Right now, my grammar, if I do a for loop for I in, say, range 10, print I, there we go. It only allows concrete numbers right here and not, say, entire expressions. So I cannot say something like a equals 10 and then for I in range of a. That gives me a syntax error. So you have to fix the grammar for the for loop in order to support that. And but the semantics of the for loop should be correct already. And you can use the semantics of the for loop to help you with the semantics of the while statements. It turns out actually that having this restriction of you can only have a constant inside of your range is actually a potentially very useful thing to do. So for example, currently how this programming language is implemented, all programs run in constant time, that we can have a proof that all programs are going to both terminate and run in some amount of bounded time. But if you allow the full range of expressions up here, then you can have unbounded runtime, no way to know what the runtime of your program is. And there are languages where you're only allowed to have some limited amount of expressivity here so that you can guarantee that if your program compiles, then it's going to run in polynomial time, say, and not exponential time. So people do have reasonable constraints, or it is reasonable to have constraints here where you can't pass variables to the range, but you'll have to fix it so that you can pass a variable to the range. Any questions on what to do for the homework, things that you need to do? Okay. Yeah, there's not really any more that I feel like I can. Yeah, question?
What about for Wednesday?
And then for, yeah, so the homework here, this is due for Sunday, and then for Wednesday, I want to read the paper. That Wednesday we'll be going over the paper. Yeah, I don't think there's anything more that I can really do on the coding here without actually implementing everything. So
You're welcome to do that if you want.
maybe so there's one little debugging thing here that I added for to this language that maybe it'll be useful to you all, maybe not, but I'll show you what it is in the last few minutes here. So there's two functions that here are built into the esolang language. Come down here. It's this print function and the stack function, print and stack. And what stack does is it prints out a list of all the variables that are currently in scope for this code. For the interpreter, wherever it's at. And so currently there's an A variable defined, and if I do something like A, I get the number 10, but if I do something like B, I get variable B undefined because it's not contained in this stack variable right here. It's not displayed as the output of the stack function. One of the things that you'll notice, though, is that this stack is not just a dictionary, so it's not just a simple lookup of variables to values. It's a list of dictionaries. And so one of the things that you can do is, or every time you add these code blocks like this, then you'll get a new set of variables being allowed in your stack. So if I do b equals 5 right here and then stack like this, it'll print out the stack. And this B right here is not in the outer scope, it's in the inner scope of this code block right here. It's in that inner scope right there, and it no longer exists. If I do after this code block closes, B no longer exists. If I do stack like that, B no longer exists, and I'll get this variable B undefined. But up here, if I can use B, and we'll actually get the value 5 out. Python does not maintain a stack for every code block that you have in Python. Most languages do, but Python does not. Python, the only time that you get a new stack entry in your stack, a new dictionary with new variables associated with it, is when you call a function. But in this programming language, as you're working on your while loop, one of the things that you will want your while loop to be able to do is to execute multiple statements at once. And so you'll need to use these code blocks in order to do that. And you could use this stack variable, the stack function inside of the code block to visualize what variables you have access to inside of that code block. With the if statement, what that looks like is if, let's say we have 0, we can have code blocks inside of our if statement. That's a perfectly good thing to do the way our grammar was structured. And I can do something like C equals 3 right here, print out C, we get the value of C right here, but C is not a defined variable outside the scope of this code block. If I do stack like this, we can see that at this location, when stack was called, C existed. It had the value of 3. But when the closing parenthesis over here ends the block, it removes this, pops this last dictionary off the stack. And so C is no longer available to us. Your assignment, one of the ways that you're supposed to test that your while loop is actually implementing correctly, works correctly, is you'll have to write some code that computes or prints out prime numbers. And so in order to do that in your while loop, you'll have to have a code block at some point. And this stack right here can be helpful just to see like what variables are defined at any particular point in time. Or it might be more confusing than is worth dealing with.
When implementing the if function, in the doc test, there aren't any doc tests?
Yeah, so I have not provided you doc tests for any of these things that you are required to implement. You are required to provide doc tests that are reasonable and demonstrate that your code actually works correctly. And so since we implemented the if statement right here, we can go ahead and implement the some doc tests for the if statement, demonstrating that that works reasonably. But yeah, all the doc tests currently pass. You will have to add more features and then add more doc tests that will also pass after you add those features. In, let's see, for class purposes here, I did my development as starting with the code and then going to the doc tests later. If I was actually working on this myself, though, I would have started with the doc tests and then done the code to make sure that the doc tests pass. So starting something like this, 0, 1, 2, I know that that should evaluate to a 1 right here because the 0 semantically is supposed to be true, and the thing over here to the left of the colon is supposed to be true. And then similarly, if I change that 0 to a 1, then the output down here should be 2. The thing to the right of the colon over here should be, we're getting false now as our input over here. And so we should get a 2. And whoops, and where was that? So yeah, I just accidentally moved the screen around a little bit, but here are the 2 doc tests that I just added. We can go ahead and double check that those are in fact passing. Oh, I'm not -m doc test.py, and they are in fact passing. And so I can add some more complicated doc tests too of, let's add some code like actual code block right here inside the condition. 1 - 1, that should give me a 0. And so this should evaluate to 1 right here. Rerun that, and oh, it's breaking. Expected a 0, got 1. Yeah, the thing over the condition over here was expected to evaluate to 0, and so we run the 1 right here, and we get a 1 value right there as the output. And now it's working, and we can also verify that we have complex a equals 2. We'll do a new letter, z equals 2, z plus 2. That'll give me a 4 right here, 4. And come down there and run it, and it passes. So yeah, you have to write the doc tests for what your while function, what your while syntax is going to do. It's not a while function. Functions are different. Functions are different than statements. It is a while statement, and you will have to define both the grammar and the interpretation of that. And because you're defining the grammar, you get to decide what that looks like. And so I couldn't even provide doc tests if I wanted to, because I don't know what your grammar is going to look like. That's a great question. Yeah.
We didn't write the code for condition. Is that because it's not necessary?
Question is, we didn't write the code for condition that's down here. It's just a pass right here. And actually, we can delete this whole thing and everything's still going to work. Verify it works by rerunning the doc tests. The question is, why does it still work? And the answer is because in the grammar right here, I put the question mark in front of condition, which says that if this appears in the tree with only 1 child, then we will remove it from the tree. And there's this distinction between a parse tree and an abstract syntax tree that you'll see people talking about at sometimes. The parse tree is the more general tree that has no transformations applied to it. Lark allows you to do the parse tree and the abstract syntax tree at the same time, doing these transformations, like removing nodes that are semantically not needed because they have only a single child. And that's what this question mark syntax does in Lark. Good question. This is a good stopping point for us. So this will be our end of class. If other people have questions, then I'll stick after and get those answered. Otherwise, I will see you all on Wednesday to talk about the paper.